Well, hello everyone, and I'm Venkatesh. Today's topic is on applications of ordinary differential equation. For that, I have taken many very popular topic, that is exponential growth and free fall object. Exponential growth of population. Sorry, popular population, quite related. Well, okay. As you know, how for that the population is depending on time. We see in here how population is depending on time, and rate of increase in population to the same quality of same quality. Uh, we see that for initial stage, that is uh, initial population. Let's do it rather than talking. Let's do this. Let's take population depending on time as p of t. P of t is nothing but population which is depending on time. The rate of increase the rate of increase of proportional to the same quality as p, then we take it as dp or dp is proportional to p, that is population. If we take the proportionality symbol, we get that dp by dt is equal to kp. Now operating dt on both side, we get dp is equal to kp dt. So if we divide p on both side, divide p on both side, we get dp by p which is equal to k dt. Well, let's integrate this. Integration on both side. We get integration dp by p. Let's write it down first. So this will be pure log p, which is equal to k. If we apply integration with respect to t, we get kt, and let's take an integral constant as a. Well, so if we apply minus a on both sides, we get ln p minus a, which is equal to kt. Now if we apply now law, we get that p by a property, one of the property of for log, and well, if we get this equation as a is multiplied here, we get as no, sorry, if we take a log here, we get e to the power of kt and divided by a, so that will be p is equal to p of t. We are taking population depending on time, so p of t is equal to a e power kt. Let's take this as equation 1. So this is a population depending on time. Let's take this as for initial population. Let's take p as p is equal to p naught. It is an initial condition. We can't take that is p represent population. We can't take it in negative form, as we can't say negative peoples or -1 people, like that. So we are taking p as p is equal to p naught as a initial population. at time is equal to 0, then we get P naught is equal to A if we apply t as 0, then we get 0 e to the power of 0 is 1, so P naught is equal to A. So if we substitute this in this equation, we get P of t is equal to P naught e to the power of kt. So that is the population depending on time is initial population into e to the power of kt. Assuming P naught is a positive, since k is also positive, P of t is increasing, that is we can write it as dP by dt is equal to kp, and is also called as exponential growth model. So this is the exact form of exponential growth model. As you know, the population is growing day by day in our country and in the whole globe. The mankind is growing day by day. We can take this and we can solve with respect to time. We get an exact answers. So this is all about exponential growth population. Let's take up a falling object now. So falling object, for falling object we have to know some of the basic idea of physics, basic concepts of physics. Let us deal with some of the basic concepts of physics. That is well, let's take velocity at first. Velocity, as you have studied in previous or primary classes, the velocity is an object of rate of change of its position with respect to the frames of reference, and it is a function of time. Actually, velocity will depend on mostly on time. And another one is gravitation. The gravitation is an force which is in Earth's which attracts everything to an object is attracted by another. It's called as a attraction force. The attraction force in the Earth which attracts every object on Earth or towards Earth, this is called as a gravitation. And acceleration, acceleration is a rate of change of velocity of an object. Change of velocity of an object with respect to time. Acceleration with respect to time is called as an acceleration, or in a vector quantity. There are some of the types of acceleration. Let's see how exactly the free falling is helpful now. To be very easyful, when we throw an object, it comes back to Earth. Here we are not throwing an object, we are just let it go as it is. When we do that, we generate an equation. Let's solve it rather than doing it. So firstly, an object is dropped from an height where t is equal to 0, and if the I will write it down. If h of t is height of object, h of t is nothing but time, and e of t is the acceleration. We are taking a of t as an acceleration, and v of t the velocity. V of t as a velocity. Yeah. So the relationship between acceleration, velocity, and height are follows. That is, a of t is equal to dv by dt. That is the rate of change of velocity respect to time, and v of t dh by dt. That is the rate of change of height with respect to time. We got this from our definition of velocity and acceleration, where and we get g is equal to minus 0.98 meter per second. That is acceleration due to gravity, and let's take it as a of t is a constant. A of t as a constant. Acceleration due to gravity can be written as dh square by dt square is equal to g. Here we are just substituting uh, here just we are substituting velocity here, hence we got d dt square is equal to g, and if we integrate this, we get let's write it down. Let's integrate. We get dh by dt is equal to, with respect to t and a constant, as c. And at an initial condition, velocity will be 0. If we take up an example, let's take this free falling object. Here a velocity is 0. If we just throw velocity, acceleration, and gravity, everything changes. At the initial stage, the velocity will be at 0, and initial velocity will be t, which is equal to 0 itself. Let's see, when time is actually 0, what happens to velocity, which is v naught in initial condition. So v is equal to v naught and t is equal to 0. Let's substitute here. We get as v naught is equal to g of 0 plus c, and is equal to c. So at initial condition, the initial velocity we get as a constant c. If we take the equation, that is dh by dt is equal to gt plus v naught. If we integrate on both sides, we get as dh by dt if we integrate, we get d. If we integrate, we get h of t and g. If we integrate with respect to t, we get that has t square by 2 plus v naught. If we integrate this, we get t plus integral constant as c. When we take initial condition has if we take initial condition here, we take initial condition that is t is equal to 0. What happens to the h here? Let's see what happens to h. So if we take t as 0, when we take t as 0, let's substitute the equation first, then let's see what happens. I think we can have a substitution here. Further substitution of h of t can, let's write it in a easier way so that we can easily substitute t square v naught t plus c. So when we substitute the initial condition we get t is equal to 0. If we substitute t is equal to 0 in this solution, we get as h0 plus 1 by 2 g of 0 plus v naught into 0 plus c. If we write it down, we get h naught is equal to c. This becomes 0, this becomes 0. Only thing which is there is c. So this is the above equation describes the height of an falling object from an initial height h naught at an initial velocity v naught as the function of a time. This is the equation. This is an equation of a falling object. So I hope it is very convenient for you to watch, and thank you for watching. Thanks a lot.